Good morning, fellow mathematicians. Welcome back to another video. Once again, video brought to you by Hago Romotschalk. Sponsored, totally not sponsored. No, it's not sponsored. Today we are going to take a look at something that many of you might find interesting, because this version of the gamma function we are going to talk about today is actually one that is kind of more convenient to use, basically just because it makes a little bit more sense if you think about it. So if you have the gamma function of z, it's going to evaluate to z minus 1 factorial. That's quite weird actually, because it would be nice to have a function which maps z to z factorial. Okay, this is a bit more appealing in my opinion. I'm not using it in a normal case because many definitions would be quite different to what we are used to, but I'm going to introduce it today, and if you wish you can make use of the pi function instead of the gamma function in further, I don't know, calculations of something that has to do with the gamma function of factorials. So let us introduce the pi function. I'm going to denote it as this ugly looking capital Pi right here, this not complete QED box of z, and like I said, pi of z is nothing but z factorial, okay? And at integer values it works nicely, so that's nothing but z times z minus 1 times blah 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 up until 2 times 1. What I want you to notice is that just like the regular factorial, so pi function right here is defined recursively, and here comes in our first definition. So if we take a look at just this part right here, okay, this is nothing but z minus 1 factorial. And like I said in the beginning, z minus 1 factorial is nothing but gamma of z. So we already have our first definition that we can use, and with this definition we can actually derive everything analogously to our gamma of z, under the condition that z is not equal to 0. Otherwise our gamma function right here would diverge to infinity. We can divide both sides by z, meaning that gamma of z can be defined as nothing but pi of z over z. Okay? So this right here in itself is already pretty cool. How can we rewrite pi of z also? Well, pi of z is nothing but, okay, if we take a look at this whole thing, z factorial is nothing but z plus gamma of z plus 1 in this case, okay? So there's also something we can do. I'm kind of improvising that. I just wrote out a few notes while driving in the bus, so we are going to define some stuff analogously that we already know about. So those are some really nice definitions right here. We can make use of some of them because, for example, we have Euler's reflection formula. Euler's reflection formula, I'm terribly sorry. What does it look like in a normal case when dealing with the gamma function? Well, we have that gamma of z times gamma of 1 minus z is nothing but pi over sine of pi times z. Okay? Now we can define this right here analogously using our pi function up here. Okay, so the cool thing is we already know what gamma of z is. Gamma of z is nothing but pi of z over z. Okay? That's a really ugly looking pi function right here, even more ugly than before. Okay, pi of z over z. But what we also have is gamma of 1 minus z. We can actually rewrite this using our pi function, because if you take a look, pi function of z is nothing but gamma of z plus 1. This thing right here is basically gamma of negative z plus 1, meaning this term in itself is nothing but pi of negative z. I hope this does make sense to you. So now we have this nice relationship right here, and now we are going to multiply both sides by z, under the condition that's not equal to 0, and then we have actually our reflection formula for the pi function. So no further stuff to do right here. So pi of z times pi of negative z is nothing but z, pi times z over the sine of pi times z. And in my opinion, this reflection formula looks actually more appealing because just we have the same argument right here, okay? Pi times z, so that in itself is already pretty cool. And also, yeah, we have this stuff right here, okay? We have pi of z times pi of negative z. I think this right here looks way cooler than the regular or reflection formula that we have right here. Okay, let us also define some other stuff. For example, we have some different representations for our gamma function, and since we have this relationship right here, this and this one, we can play around with this a little bit. So let's at first start off with the integral representation for our pi function right here. It's your boy, the pi function. So pi of z is nothing but, okay, gamma of z plus 1. And if we plug this in to our integral definition of the gamma function, we are going to get an integral from 0 to infinity of, in the normal case, for example, t to the argument minus 1, so z plus 1 minus 1 is nothing but z, times e to the negative t dt. And this right here looks a bit nicer, in my opinion. I mean, if it weren't too convenient to use the gamma function, I would definitely be in to use the pi function, but I'm just too used to using the gamma function right here. So this is our integral representation, so no need to use our boy gamma of z plus 1 anymore. We can just use our pi function. We also have two other definitions. On the one hand, our Euler definition as an infinite product and the Weierstrass definition. Let us start off with the Euler definition right here. For this, we are just going to make use of the fact that we have gamma of z times z is nothing but pi of z. Okay, and this comes in really handy because pi of z is thus nothing but z times the Euler definition of our gamma function of z, which is nothing but 1 over z, and then we have this infinite product. Our infinity is spreading its legs, its beautiful pi legs right here. Okay, I'm writing this capital pi like this just because I want to distinguish it from this pi notation right here. Then we have 1 plus 1 over k to the z power over 1 plus z over k. And this should be it. This, in my opinion, is the Euler definition. And you see the magic happening right here. This and that is going to cancel out, and what we are left with is just this beautiful thing right here. Okay, we are always going to get rid of some factor that we would have in the normal case when dealing with the gamma function. How can we also express this right here? Well, we also know the Weierstrass definition. Okay, so this right here is nothing but z times. Okay, in the Weierstrass definition, in normal case we had 1 over pi of z. It's just dealt with gamma like this because we have that it converges then everywhere in the complex plane. So this thing is actually analytical, the reciprocal of the gamma function. So we have z times, okay, now thinking in reciprocal terms, we are going to have 1 over z once again, this and that's going to cancel out, that's pretty cool. And then we are going to have e to the negative Euler-Mascheroni constant times our infinity-grill. Yeah, 1, not 0. And then we are going to have, let me see, e to the z over k over 1 plus z over k. Yeah, this is how it is. Okay, this right here is thus our Weierstrass definition basically of our pi function right here. What other cool things can we actually do? Let me think for a second. Like I said, it's kind of improvised. We were going through those definitions and this right here. Oh yeah, our boy the beta function, for example. We know that the beta function of x comma y is in the normal case gamma of x times gamma of y over gamma of x plus y. Now we can rewrite this right here equivalently because we have this relationship right here, okay? Meaning that this thing is nothing but gamma of x over x times gamma of y over gamma of x plus y over x plus y. If we take the reciprocal and all this crazy stuff, we are going to be left with pi notation. I'm terribly sorry. Pi, not gamma. Okay, we are going to be left with, this is x plus y over x times y, and then we are going to have all the other stuff left, okay? I mean, this in itself looks pretty quite cool. And one cool thing you can immediately see is that we have this thing right here being nothing but, it should probably be the, yeah, if you plug those definitions in here, this in here, you are going to be left with the series expansion of the beta function. I don't know if I have made a separate video on that. Okay, so we have this stuff right here. It's more of an improvised session, like I said before. And maybe there's one last thing I can actually take a look at. I mean, we have covered this and that. We have the beta function, we have this chunk. Is there anything left we can actually do? Is there anything left we can do? Let me take a look at what I wrote out in the bus. Maybe I can spot something that we haven't written on here. Oh yeah, it's your boy, the digamma function. So digamma function, in this case, is nothing but, so if we take the natural log of pi of z, we know that it's nothing but natural log of gamma of z plus 1. Okay, that's the last thing I would like to cover. Meaning, we can thus differentiate both sides. Meaning, we are going to get this thing right here. It's kind of the digamma function, you could say. I'm going to denote it like this, of z. But in any case, it's going to evaluate to the digamma function of z plus 1. Okay? But what we can also do, we can rewrite this thing right here as nothing but the natural log of z times this right here. Okay? Which is nothing but the natural log of z plus the natural log of gamma of z. And now we can simply differentiate both sides, leaving us also with, okay, 1 over z plus the digamma function of z. Okay, so this right here is basically just our digamma function of z plus 1, and we can also rewrite it like this right here. And also in my introduction to the digamma function, I found a nice formulation for this thing right here as an infinite sum. And at integer values, it's a nice telescoping sum. I made several videos on that, checked it out. Maybe the links are going to be in the description. And that's basically it. So, yeah, it's more of just plain talking right here, because we have found out a lot of things that have to do with the gamma function. All we really have to do is to apply this definition of the gamma function to our pi function right here. And then we are through with all of this. I thank guys for watching. Hageromochak, my boy, my good boy. If you did enjoy this video, please like and subscribe and recommend the channel. If you like, if you want to support channel a bit more, buy those t-shirts I created, or support channel on Patreon. No matter what you do, I thank guys for watching. I'm until the next video. Have a flammable day. See ya. Ciao. Auf Wiedersehen.